Welcome, everybody. My name is Armin Sobani, and this is my email if you want to contact me later. This is the first talk in a series about using modern C++ for high-performance data science. The whole series is available as an executable book here at this URL because as it's quite long, as you can see. Here is the QR code to make it easier for you to connect to the site. You can use the site as I progress to check the content. So why on earth you need to use C++ for data science? I think those of you that are already active in data science, they especially adore Python and use it for the regular day-to-day things. But let's see what each of these languages, C++ and Python, can offer to a data scientist. While Python is the king of the hill when it comes to ease of use and also community and libraries, when it comes to performance, concurrency, and memory management, which are the pillars of high-performance computing, C++ is still the throne. It's quite important because, for example, aside from performance, which is for C++ is a compiled language, so it's more or less faster than Python. But concurrency is a really important thing these days because, for example, most of your laptops or even your mobiles have several cores that can participate in computing, but Python's the so-called GIL or global interpreter lock prevents it to use more than single thread. There are some workarounds around it, and there are libraries that work in parallel. But the C++ in the core standard provides concurrency and parallel algorithms, each in the different standard. But the whole thing, or the whole message is that, or the word of advice is that stay with Python unless you hit the performance wall. But once that happens, what should you do? Because for a data scientist working with Python, there are numerous tools and things that you are using them, and most of them don't have a corresponding the one in C++ ecosystem. So these talks are designed to help you find some of these tools for your day-to-day data science thing with C++. In the first talk, we covered C++ rapid prototyping and plotting with G3P. And if you wonder what's an executable book, you will find out for sure today. So we start with rapid prototyping. C++ with a compiled nature in this regard is kind of lackluster because rapid prototyping is really important in programming and in data science because you want to start with something, tinker with the data, and try different methods to see which one works, the different charts and plots to do the analysis and those things. And this compiled nature of C++ prevents it. And Python, because it's an interpreter and also has the Jupyter notebooks and those things, shines in this area. But the modern C++ is not your grandma's one. As you can find later during these talks, C++ can did actually some catching up, and we can start using some of those features. So if we want to do rapid prototyping using C++, at first we need a C++ interpreter, which is already checked. Cling is an interactive C++ interpreter developed by CERN in Europe, responsible for that, particle accelerator, as part of the root project, another software project that it was part of it. It's built on top of LLVM and also Clang libraries, and it provides a REPL and also uses just-in-time or JIT compiler for compilation. If you manage to use one of the newest version of this Clang, it also supports NVPTX for CUDA code. We are going to demonstrate that actually today in an interpreter environment, and all the parallelism like OpenMP and those things works right in the interpreter, which is quite nice. But it's not enough. We also, in order to work in a Jupyter for notebook, for example, we need a Jupyter kernel based on Cling, which Zeus can do that. There are usually, Jupyter kernels are based on traditionally IPython or Zeus. Zeus is a newer one. Is a C++ library that facilitates the implementation of kernels. There is also a Jupyter kernel for Python implemented with Zeus. The good thing about this version, if you are interested, is that it natively supports debugging on Jupyter. So as you know, maybe by now, that Xeus-Cling is one of these interpreters or kernels. So if we combine the Cling interpreter with Zeus, we come up with Xeus-Cling, which is a Jupyter kernel for C++ based on Cling as the C++ interpreter. We use Xeus-Cling throughout this book to work with our C++ codes interactively. So let's start with our setup with Xeus-Cling. If you want to start working with Xeus-Cling, actually, there are different ways. The easiest one is using Conda and Mamba environment. In that sense, you just need to make a virtual environment named Cling using Mamba create -n Cling, and then activate that environment, and then using Mamba installing Xeus-Cling from the Conda forge. And then you can run the Jupyter lab and start working in Jupyter. If you, like me, you're not a fan of Conda or Mamba, and also more adventurous, you can choose to make an Python environment rather than using that. Why I don't like Mamba or Conda is because of their fat interface. You have to install lots of libraries and those things, and it quite takes some space. And my laptop with only half a terabyte is already full. So this one, if you're interested to do this path, I developed a bash script that can automate the whole process for you. It's really easy to run it, but it requires a Linux environment. But on Windows, for example, I already did it on WSL and it works quite fine. The only downside is that compiling the whole Cling is really time consuming. It may take hours. On my laptop, it takes about 45 minutes to do the whole thing, and you need lots of memory, and these are some recommendation if you enable the threading and those things. This script also supports the threading, but for example, on my laptop, I don't go beyond 2 or 4 for this. It supports also making the Docker images right from it. So if I want to show you how it works, I've already done that. It's just running the script and it does all the things in the background. But once it's finished, it also makes there is an option that to install the whole thing in a Python virtual environment. Once it's finished, you just need to source. And for example, I install it in this path, Xeus-Cling environment, and then activate the whole thing. And then you can do Jupyter Lab to start it. Once it's started, you can click on this link to open the whole thing. You can see that there are some variations here. If you go with the Mamba thing, you can only see the kernels for C++ 11, 14, and 17. But these are the additional things that you can find if you go with this script. It supports also CUDA and also OpenMP. So to open one, you just click on that. There are some samples here that we are going to go through them, but I wait a little bit first and then come back to this again. So the last way to run the whole thing, using the same script, there are some Docker container images already produced, one for without CUDA and the second one with CUDA. If you want to run those, you can try this command. It's pretty the same interface, and it has all those notebooks already inside so you can explore. If you want to just use the CUDA version, this option is necessary. And one other thing, if you want to open your local notebooks inside the container, you can map your current folder to the home folder of the image using this option. So in that way, you can access your notebooks that are outside the container. Another option on HPC cluster, for example, on our cluster, is to use AppTainer. If you use AppTainer, by default, it mounts the current folder as your home. So it's like that. And this is the CUDA version that you can go with it. Next thing that we are going to explore is the basics. So here, now you can see what an executable book is like. You can see a power button here. The whole container is available on Binder. So you can see if I switch to the first page, you can see the link to launch the whole thing on Binder. I can actually do that here for the sake of demonstration. If you do that, it's because it's already cached. It should be quite fast. And once it's done, you end up into the same Jupyter interface, and you can find these notebooks here. So you can see that the kernel here by default here, I already done that for you, is C++ 17. And if you want to run them one by one, you can do that. But in this executable book, you can also run the whole thing on this page. The only difference is that you can just run the cells. You cannot edit them. So if you want to do that, you just click on this. You see the connection to the binder here, the latest status. And once it's done, you can do the same thing here. So for example, the first thing that we learn is that because Xeus-Cling is an interpreter, there is no need for main. Yay. You just start typing things and it happens like Python. So the next thing is that you can display the rich content, anything, for example, images and those things. by just omitting the semicolon after the name of the object. So for example, here, this one is the pre-generated output for the web. But if you want to actually run it, you can see the results actually run here and then check that. So, and you can run all of them together like the Python notebook by clicking on this as well. But you get the whole idea about how to work with this. I'm going to switch now, but it makes no difference. I can run it here as well. One more thing that I want to tell you is that on some of these pages, do you see this Python as Jupyter logo here? It means that there are some executable cells in this page that you can decide whether you want to run them on this computer, on this web page, or switching to the container image on Binder or Docker if you want, for example. The next thing that is interesting about this Xeus-Cling is this feature, declaration shadowing, which is really important for working with C++ codes. The thing is that based on the ISO standard, if you have some function like this, and later you want to do some exploration and then the next cell or some cells down, want to change it to this, it will complain about that this footing is already declared and it shows error. You have to stop the whole kernel and then skip those cells and go to this, which is kind of annoying. But Cling has this feature that you can do this, enable these redefinitions. By default on the Jupyter notebooks is on, so you don't have to it. But anytime that you want to disable it, you can use this command to make it enable or disable. So one makes it enable, which is on by default, but you can pass 0 to disable it. But it's really handy, and later you can, during the plotting with G3P library, you can see that it's a lifesaver. And another thing is that because it's an interpreter thing, those standard libraries are already and headers are there and linked. But if there are some third-party libraries, you can do that. If you want to add to include path, you use this pragma syntax. And if you want to add a library and then load it, you use this syntax. We will show you how to do that later. We have some magic comments as well. One interesting one is like magic comments on for example, Python, Jupyter with Python kernel, but a little bit different. So this one is quite interesting. Person executable can turn all the cells, previous cells, into one executable file, and you can run it as a compiled one. But no matter what I throw at it, it didn't work out. I don't know if some of you later or now know how to make it work, but for me, it just shows writing executable to the file and then says could not link executable, and then it cannot find this file. So it's a really nice feature, but I couldn't make it work. But this one is quite handy as well, and it works. You can just do like this. You just dump the content of the cell to a file, and you can actually also append to it using the -A option. So here you can see the output like this, and the final file is like that. And at any time, using for example, this one, or I try to run the whole thing here now to show you that it actually works. This one is the executable one that I told you. And these are the output of other things. And I can do it on my computer as well. But because I've already showed you on the binder, no need to do that again. This one is quite handy. It's the same as the one that you can find with the Python, but the name is different. It's time it. Time it for one line. And if you want to do it for the whole cell, you can do time it. There are some other variables that you can, options that you can change. Here you can see that it's a number of loops and also the number of repeats for each loop that you can change. It's automatically, dynamically change these variables based on the time. So that is not a fixed one. But if you mention them, it's going to use those fixed numbers that you mentioned. So there is an extensor library, which is already included in the image that I provided. And it's quite nice, something like, for example, NumPy in Python, you can use. And these are some samples that you can see for the timing evaluation and those things. And here you can see the results as well. The next thing here is that you can see that the whole parallelism actually works here. This one is a C++17 parallel algorithm using the Xeus-Cling. Before running this, you should make sure that the kernel is C++17, and you need to include the execution header as well. But one thing that we should do before that is that because the parallel algorithm on both GCC and also Clang are based on, under the hood, the threading building blocks, Intel threading building blocks doing that, does the whole thing. You should link with this library. So you need to do this pragma cling load to load the libtbb in order for it to work. And then this sample shows the reduce one. The whole documentation of this page automatically generated on GitHub using the GitHub Actions. GitHub runners are usually run on 2 cores. So when you run this, here is the timing for the reduce using 1 core. You can see the timing is about 188 milliseconds. And this is the result for the parallel one on the GitHub runner. You can see that it's even better than twice. And the part of the reason is that the TBB reduce algorithm is really efficient. And part of that is also part of that is even faster than twice, even close to 3 times or more, is that on JIT compiler, the parallelization has a better effect maybe. And this is the result because the reduce returns the summation, but we can't do it in the time it loop. So I omitted here, but in order to show you that it's actually correct, you can check the output here. So it was on the GitHub runner, but let's see on my, if you try to run this on this page, these results takes even more because the binder has only 1 CPU or core. I can make it run here. Let me show you. And you can see when it changes here, the parallel version is actually takes more. This is for the single, it's sequential, and the parallel version, it takes more. But on my computer, it has more core. Let me run this here. So you can see that C++17 is here, and this is shows that the kernel is busy. It takes more than it should. Maybe something is wrong with. Let me see. Oh, no. It's always like this. When you want to demonstrate, it doesn't work. So something is wrong. Let me maybe too much of threads. Okay, let's try again. Yeah, this time it works. Let's see. Yeah, and this is the reduce using the parallel execution policy. So it takes time because it does it for 7 runs and 100 loops each. So you can see that 94 milliseconds came down to 17 now. And this is the results. And the next thing is OpenMP. For OpenMP, again, you have to make sure that the kernel is C++17 OpenMP to activate the compiler option, actually the interpreter option. And another thing is that you need to, again, load the libomp dynamic library for this to work. Here are two parallel template algorithm for a simple vector add, one using OMP parallel and the other one without it. You can see that the only difference is adding this pragma thing, and that's the whole beauty of OpenMP. With single line of code, you can make your code parallel. And again, on GitHub using the runners, you can see that here vector add and results and the timing for the OpenMP. Here is more in line. You can see that this time cut in half here. So it shows that these two cores in the runner is actually there. And if I show you the version on my computer is more or less the same, but a little bit maybe fast. The last thing that I want to show here is working with CUDA. So here works, but I disabled the cells because when it runs on binder no way has any GPU or things. So you can run it on that. So the output is only for the CPU lines and not for the GPU. But I can run it on my computer. So here, like ordinary CUDA code, you can include the headers. And here I ask about the CUDA device to see what's the name. You can see that it returns NVIDIA GeForce RTX 3050 laptop GPU. And here is our vector add using the CPU version. But this one is with the double. The OpenMP was with the float ones, 362 milliseconds. And here, this is our kernel for the CUDA. You can see that. And here the allocation of the whole thing and calculation of the threads per block and blocks in the grid for our kernel launch parameter. And interesting thing here is that you can see that the kernel launch syntax, which is not standard C++, is supported by Xeus-Cling. But because it's non-blocking, we have to use CUDA device synchronize to wait for it to finish. And you can see the timing from 362 milliseconds came down to 14 milliseconds. And then we need to free the memory. And the results, we can check the results, which should be 2 plus 1 for each cell to 3, which is correct. And then free the thing. So it shows that the whole thing works here. And we can use all these the available cores or GPUs at our fingertips while on our Jupyter notebook with C++. But the next thing is that usually in the data science projects, it's not only calculations. We want to analyze all those data and turn them to some charts and plots. So Xeus-Cling, as I said, supports displaying rich content, but you need a C++ library like matplotlib that supports that. So you can find some projects on GitHub for that, but some of them, like for example, XPlot is completely abandoned. It's not, nobody worked on them since 5 years ago. And some of them like XVega are on early stage for a long time. So back in 22, I wanted such a library for a project, and I couldn't find any. So I start thinking of a quick and dirty hack like the one here. Actually, it was in the issue. There was a suggestion how you can do that. I wanted to do something like this hack, but on that time, I attended the SharkNet General Interest webinar by my colleague Baulai about real-time display with GNU plots. So the whole idea sparked on my mind to use GNU plot at the back end, and a library named G3P was born. So this is one of the many benefits of attending these webinars. So here we have the G3P library. We switched to whole documentation for that to see how we can produce plots using C++ on Jupyter Notebook using Xeus-Cling. So G3P, which is the name comes from GNU plot plus 3P in it, so G3P, is a tiny header-only modern C++ interface to GNU plot, but it can punch over its weight. It's really tiny, but it's really powerful. So these are some of the nice features of it. It supports rapid prototyping with Jupyter. You can, with very few line of codes, you can generate very beautiful and sophisticated plots. And the whole power comes actually from GNU plot, because GNU plot is really, really powerful scientific plotting. And there's so many, for example, it's the engine behind the octave plots and those things. And there is nothing that you can't do with GNU plot, I think. Anything that comes to your mind, you can do it with GNU plot, but to figure it out how. Another nice feature of G3P is that it supports several techniques for putting animations into Jupyter notebooks. So for example, it's a simple plot here. You can combine the for loop of C++ with new plot and have something like this as a GIF animation, for example. And also, if you combine this method with XWidgets, which is a C++ library based on IPy widgets, you can have interactive plots in the Jupyters like this one. And the last thing is that it supports both, G3P supports both C convention, as you can see here. You can pass the parameters like this one using a format like printf, and also C++ version or convention, which you can use the stream operators to pass the parameters to GNU plot. And this is the same code with the GNU plot that generates this output. Other features that I can mention here quickly is that this multi-platform is header only and only one header file. And there is only 300 lines of code excluding the comments. So let's get started with it. The whole process of working with G3P, G3P doesn't necessarily need Jupyter. So you can use it in your project, compiled projects, and generate all kinds of plots. In order to do that, the only thing that you need to do is to include that single header, which is released here or here, and start to work. But usually it's better to use the CMake to install the whole thing. And this is the procedure to do that. And also G3P exports the namespace CMake target, G3P : G3P. So downstream applications can use it. So if your project also relies on CMake, the best way to use G3P is just to include these 3 lines of code, or you can even use the embedding with CMake. You can, starting with, if you rely on CMake 3.14 and higher, you can first check whether, with including the fetch content module, you can first check whether G3P is installed or not. And if it is not installed, it tries to fetch it from GitHub and then make it available. This is the easiest way to include the G3P support in your code. So for rapid prototyping with Jupyter, it's the same. You can, if you rely on Conda and Mamba, first you install it in a Cling environment, and then using this line, you just download the header file and install it in the Mamba. You use Mamba environment, this command, to see the folder for the Cling environment. And then using this command, you can install it there. And then G3P will be available. And or the next thing is creating a Python environment and then install it like the way that we did it, or using the Docker images here or Aptainer. These are for G3P and have G3P already included. So to start working with G3P, as I mentioned, the only header file that you need to include is this one, G3P GNU plot. Once you did that, you can start a new plot instance, which is defined in G3P namespace like this. For example, in this example, we named our new plot instance GP. And then you can use the C or C++ convention, or even mix and match them. It's not necessarily, you don't need to stick to one of them. For example, for this one, you can see that part of it is in C convention and part of it is in C++ convention, depending on your needs. So here is a simple plot. You can see that those plots are already can be automatically generated even on the web page. But if I want to show you here on my computer, I can go to G3P folder here. And if I want to show you this, I just need to restart the kernel and run it. This generates the plots here. So you can see that it's works on both web front and also inside the on the Jupyter. There are some things that you should get familiar with it. The first thing is that once you generate a plot like this is a simple example of new plot. You can find all these plots here. It's not bad because the good thing is that there are lots of plots, and usually when you want to do that with GNU plot, the best thing is to first check one of these samples and see which one is close to what you want, and then start to change it to get the final results. But we started with a simple one, which is like this, and in the C++ convention is like this. The thing is that when you are in the Jupyter notebook, the good thing is that you can explore easily. So if you change the count here, for example, count number, you can see the results. Your plot is going to be coarser and coarser like this. But you see that the whole thing works. But the thing here is that to display a plot, the only thing you need is to have the last object without the semicolon. Because most of the methods on G3P returns their constant reference to new plot object. When you omit the last semicolon here, it means that after doing this, show the plot in the Jupyter. And that's why when you do like this, it also shows the whole plot here. But if you want to explicitly show a plot, you can also use the G3P GNU plot, or also XCPP, which is part of the Xeus-Cling package display, to show the object like this as well. There are some rules here that because we don't have time, I just skip. You can go through them to learn how the whole G3P works. But two more things that are important here is first embedding the plot data. So those examples are using the features in GNU plot to generate the plots. No data came from C++. But when you use a library like G3P, the whole point is to generate the data in C++ and transfer it to GNU plot to print it. In order to do that, there are two ways. One is inline data. If you use the special file name dash, just after the plot command, for example, splot or plot or those things, it means that the lines immediately following the plot command are interpreted as inline data. So for example, here is the MATLAB's pick function. The whole function is like this. This is the implementation as a template function in C++ here. And if we want to plot it using the G3P, here is the code snippet. These are the preparation of the chart, the parameters that we like, for example, the colors and those things. And here, when we want to plot the data, we use this dash to tell that the data is coming after this command. And after this line, we can use a for loop to send the data, which is generated with our function in this way for x1 and x2 and the function results. We use a nested for loop to send this data to to GNU plot. And after it's finished, we need to use the GPN to tell that a stream is done. And this is the final results of the plot. But the second way to do that is using the data blocks. Usually, once you have, for example, a huge data sent to GNU plot already, you need, most of the time, you need to use it again. So it's this method is not really good for that because each time you need to send it again. So using the data blocks, once you made a data block, you can use it several times, for example, in multiplot to send it, use it in the GNU plot. In order to do that, G3P provides a helper function, make data block for you. So here, the whole thing, we first put the whole thing in a container, in a vector, using the same loop function, but this time we just put it in a vector like this. Is a single dimension vector. And then we use the make data block and providing the parameters. Because the grid was 40 by 40 and 3, we provide these parameters. And if you wonder what are these parameters, you can check the function documentation to see what are these. But once we have it this as a pix, it turned into a data block. And we can send it several times. So here is a multiplot that first we plot the same thing, and then we do a counter map here and send the same thing again. But this time the data is already sent to GNU plot. We don't have to send it again. We just refer to it like a reference. And this is the finished plot. And one more thing, once you do a multiplot, if you try to display it again, it just displays the last plot. So for multiplots, you need to, if you want to display them again, you need to do the whole thing again rather than, because for the multiplots, the last one only with GP shows up. And the last thing is animating plots. So you can, in GNU plot, there are different output formats, which in GNU plot terminology is called terminals. By default, when you run GNU plot on a desktop computer, the terminal is Qt terminal. It shows up. But for the Jupyter notebook, G3P changed the default terminal to ping Cairo. So it can be embedded into the Jupyter. But there are two animation formats. One is GIF animation, and the other one is WebP. But WebP is only supported by GNU plot version 6 and higher. The image that I provided actually has the GNU plot version 6. So we can also use WebP as well. So here is the same example, the sinus sine, the sine plot, but we used it in a loop to make an animation. By changing the terminal to GIF, you can have something like this. And if you want to change to WebP, you just need to change the term to WebP. But there is a problem with the missed version, support for WebP. It converts all the animated WebPs to single frame ones. But no problem, if you want to see it in action, we just need to run the actual one, and the WebP version also works. So here is a good example of running this on the web page. So if I run the whole thing now, it actually generates them on the web. So this one works. This is the GIF animation. And this one is the WebP animation. If you click on this and save image, you can see that it's actually the extension is WebP. And the third way to do this is using the G3P display in a loop. If you do that, it works, but the problem is that it can't be run as an endless loop. It just actively runs. So if I, for example, run it again, it runs for the time of the loop and then it stops. But we can use the same technique here to do the interactive plots. This one is an example of doing an interactive plot using X widgets. The only thing that we have to do is to turn our GP plot into a X widget image. So we just change this to this one, and then later we can register an observer for it to update it depending on the value of a slider. So if I run this one is the actual one running on the Jupyter backend. You can see that it works. So it works both on the website and also if I run it on the Jupyter notebook, it's, oh no, this one. It also works here. Let me do that for the sake of demonstration. So these animations sometimes take, oh, let me see. I think I have the same problem here. I need to run it again. Maybe something here is going on. But it actually works like this. Let me see the time. We actually finished, almost finished. The last thing here is some troubleshooting. The good thing about the G3P is that it has a two-way communication with GNU-plot. So you can send commands to GNU-plot and also you can get it back. So you can check for some of the things like version and those things. And you can also send some of the commands to GNU-plot and check the output returned by GNU-plot as well, which is really handy for debugging. And the last thing is a gallery of some of the things. So for example, the G3P logo is actually generated with the same code with G3P here. And also here is another animation, which came from GNU plotting org. You can check.